Nothing happened. No, now. Hello and welcome everyone to today's webinar, Stamping 101 Fundamentals. I'm Mojmír Kučera, a technical consultant specializing in manufacturing process optimization and tooling solutions. And with me today is Peter Ulintz, a metal stamping expert with over 37 years of industry experience. Hello, Peter. How are you today?
I'm well. Thank you, Mojmír. Thank you for having me today.
Great. Thank you very much. Before we dive in, let's make this session interactive. Feel free to introduce yourself in the chat and share where you are joining from. So you can see in the right corner comments. So if you would like to comment, you can comment. You can do it as exactly I will show you now. So feel free to introduce yourself in the chat and share where you are joining from. You can do it, or it's up to you. You don't need to, but I just want to show you where the comments is. Okay, so today we will be covering the key principles of metal stamping, focusing on stamping fundamentals, material behavior, tooling, and die design, and common challenges. At the end, we will have a live Q&A session, so feel free to drop your question in the chat. And okay, so let's start with the basics. Metal stamping is a high-precision manufacturing process that involves cutting, shaping, and forming metal sheets into components using dies and presses. This technique is widely used in the automotive, aerospace, and electronics industry due to its efficiency and repeatability. And at this point, I'd like to hand it over to Peter Ulintz. So Peter, the floor is yours. Go on, please.
Okay. Thank you very much, Mojmír. Thank you, everybody, for joining today. This is really quite impressive. We have many people from all over the world joining us today for this webinar. So I thank you for your time. For those of you who don't know me, as Mojmír said, I've spent over 40 years in the metal stamping and tool and die industries. About 10 years ago, I left the industry to work indirectly for the industry through the Precision Metal Forming Association, which is an association that represents metal forming companies, primarily in North America, but we do have members from all around the world. In addition to that, I am a monthly columnist for the Metal Forming magazine. I write a monthly column called Tooling by Design. I've been writing that for nearly 20 years now. If you find some of the information that's presented here, I'm sure I've written something about it. Just visit metalformingmagazine.com and just look for the Tooling by Design articles. All right, let's talk about some key fundamental stamping processes. You know, if we think about stamping dies and we think about what a die can do, they can basically do two things for us. They can cut in some manner, and that cutting can involve trimming, blanking, punching, or perforating, depending on the term that you may use. And they can do forming. Now, forming could be in the form of bending, deep drawing, or what we refer to is just crush forming or crash forming, or just simply forming. So when we talk about these key processes have some key parameters that we have to be aware of. And they're important to discuss when we're talking about metal stamping 101, because these are things that everybody is going to encounter immediately when you start dealing with stampings. So in terms of blanking and piercing or punching, the number one critical parameter in that process is the alignment of the punch and die. The punch and die needs to be aligned. Now, when we talk about punch and die, I have, I don't know how well this shows up on the screen, but I have a die matrix and I have a punch. And the alignment, the way that this punch fits into the die matrix, must be precisely aligned. The punch cannot enter on an exaggerated angle. It must be exactly perpendicular. And things to be aware of are the fact that the die could be properly aligned when we have it in the die shop, but when we put it in the press, we may experience some misalignment. Now, that misalignment can come from a number of things. The ram might not be parallel. So if the ram's not parallel, the upper punch is not going to be perpendicular to the lower die matrix. The ram gibbing might be loose. So the ram can actually move side to side, which can affect cutting clearances. You may have a die that looks perfectly aligned when you have it in the die shop, but as soon as you set it in the press, you're experiencing punches that are chipping or shearing, and that could be from this side-to-side motion because the gibs are too loose. Another source is what we refer to as tipping moments in the die. So I have a pad of paper here. This is my die. If I have a high load working over here on the die, especially a progressive die, that generates a larger load, it's going to want to tip the die. So when that die tips, the punch that's mounted on this side over here is going to tip as well. So we're going to have this tipping moment. Even though the die in the die set is aligned, the press is causing some misalignment. And a lot of times, if the press isn't maintained well, these things are not considered. And what I believe is one of the things that a lot of die maintenance or die repair people struggle with is we see, because our training is in the die, we understand the die thoroughly. We know all about the die and how the die works. So anytime there's a problem in the press and we're not getting a good part or something is happening to that part that needs to be fixed, where do we look first? We look into the die, because that's where our training is. But we have to remember the die is just one tool in a global process. We have a press, we have a feed, we have a straightening system, we have lubrication, we have thermal interactions inside the die. Die sections heat up, clearances change. It's a very interactive process. Now, when we're looking at bending dies, and we talk about bending, talking basically 90-degree bends, one of the challenges that we often run into is spring back. So we take a piece of sheet metal and we bend it at room temperature, it is going to experience some degree of spring back. I've had people ask, how can we get rid of spring back? Unless you can change physics, you cannot change the nature of spring back. It's going to be there. But what we can do in the die is control spring back. And we can do that through a number of ways. One of the most common ways is coining the bend radius. So when I refer to coining the bend radius, we would hit the bend radius, and usually we're hitting a little bit past the radius, more towards the flat section of the bend, to force that to bend past 90 degrees. We put a little relief on the lower die to cause that to bend past 90 degrees. And it can be very effective. But the one thing I will caution you on, especially if you're running progressive dies or any die that has stations that are hitting home, once you have the shut height set correctly in your die, now the shut height is set correctly when you have pads that are hitting home and you are closed on whatever material thickness that you are using. As soon as you are hitting home in that condition, your shut height is set. If you have to hit the bend radius harder, or if it's overbent and you have to back off of the bend radius, you have to shim or remove a shim from the bending punches, the forming punches. Do not change the shut height. Once the shut height is correct for the material thickness you are using, that's what it is. If you have to make any adjustments in the die, including stencils, you need to shim the stencil up and down. Now, the only exception would be, if you're adjusting for stencil depth, would be a blanking die, or just a die that's doing cutting, because you have no stations that are hitting home. So if you're not hitting home on the material in the die, you do have some flexibility to make shut height adjustments for those forming depth. Drawing is a unique forming process. It is a process that we refer to as a compression tensile mode of deformation. If you think of a deep drawn article like a cup, a cylinder, many times people think that all the deformation is taking place in the sidewall, that the sidewall is being deformed and stretched. But in reality, it's not. In reality, all of the deformation in deep drawing occurs in the flange. So as that flange is being compressed, it's actually thickening. Now, I have some slides that I can show to illustrate this better, but what I'm going to do is wait to the end of the presentation to show those to you. But what's important here is to realize, because the nature of deep drawing process is material in the flange will thicken, that thickened material will end up in the sidewall of the article, and additional die clearance is required. So we can't simply offset the clearance between the punch post and the die cavity by material thickness. We have to allocate for the thickening. Some materials, mild steel, for example, and some high strength, low alloy materials may increase in thickness 10 to 15%. But you get into some austenitic stainless steels and you'll see the flange thicken as much as 40%. So if that sheet metal is getting 40% thicker in the flange, when it bends over the die entry radius, if there's no clearance for the material to get in there, that's what causes the sidewalls to stretch and eventually fail. So a very important parameter that we have to keep into consideration. Now, when I began my apprenticeship, I guess I failed to mention that I'm now retired. I do these things, webinars and seminars and things, on a consulting basis, or like today, just for fun, just because I enjoy doing it. But when I was trained in the tool and die trade, that was nearly 50 years ago. It's the 1970s. So we didn't have CAD systems. We didn't have CNC machines. We didn't have wire machines. All of our training as a tool and die maker was really in machining. We were a jack of all trades in terms of machining. Everything was about the die, how to machine the die, how to assemble the die, make sure the clearances are correct, how to tweak the die to get a good part. And one thing we never learned about was the material that we're deforming. So when we're building dies, we think the final product is the die itself, but it's not. It's the stamped part. So we have to ask ourselves, if we could talk to if the die could talk, the die would basically ask, material, what properties do you have? How are you going to spring back? How much stretch or ductility or formability do you have? How quickly do you work harden? What happens if I form you faster? Do you get stronger? Do you get weaker? As a die, the die needs to know these things because it has to be designed to accommodate the behavior of the material. And for many, many years, especially before the advent of forming simulations, we had everything backwards. We built the die and then we asked the material to behave the way we wanted it to in the die, not realizing it has its own behavior and it's not going to change because we need it to act a different way. So it's really important to understand properties such as elasticity, because this is directly related to spring back. And as materials get stronger or higher in strength, spring back is going to increase. We saw this very quickly in the 1980s when high strength low alloy materials started really becoming prevalent in the automotive industry, where we would typically have to put in 1 to 2 degrees of spring back compensation for bending. Once we got to these materials, we were, depending on the strength level, 3 to 5 degrees of overbending. With the advent of some of the advanced high-strength materials that are in the marketplace now, studies have shown that some of these materials require 15 to 17 degrees of overbending in order to get a vertical angle after forming because of the high amount of spring back. That, my friends, is going to change how you design your dies, right? We can't approach these new materials with the same guidelines and the same experiences that we have with mild steels or the traditional high strength steels. We also need to understand the formability of materials. Back in the 70s, like I said, we designed a die. We expected the sheet metal to make a part to print. Our contention was the die's right, the part's not, must be the material. So we're on the phone calling the material supplier. Very common back in those days. But now with the advent of material testing and material formability and simulation, it's hard to blame the material. Usually if we're not getting the results that we're looking for, we haven't designed the die to accommodate the behavior of the material that we're working with. 2 other parameters are work hardening and strain rate sensitivity. Some people have said they would like a material that doesn't work harden. You may have heard that yourself. You may have even uttered those words. But something to think about. If the sheet metal did not work harden, you could not form it. Now, we relate work hardening to a material parameter called the N value. And some of you may be familiar with the N value. N values are typically small numbers. They may be anywhere from 0.18 to 0.24. I've seen some stainless steels with N values exceeding 0.35. These numbers may not mean anything to you if you're not familiar with N values, but I share that to make this analogy. Toothpaste has an N value of 0. How well can you form toothpaste? So we need the work hardening capability. So we need to understand how the material work hardens and its sensitivity to strain rate. Mild steel, for example, if I run a stamping die with mild steel, if I turn up the speed of the die, because of the strain rate sensitivity of mild steel, it has a positive M value. With an increase in speed, the sheet metal is going to exhibit an increase in strength when I form it faster. Now, aluminum, on the other hand, because of its negative strain rate sensitivity value, it has a negative M value. As I form faster, the material gets weaker and more likely to fail at higher speeds. So these are parameters that we have to understand. So now we've got a little bit of understanding of the different processes, cutting, bending, forming, and drawing, and the roughly different materials. We know materials are different and they have parameters or different behavior characteristics. Now we have to take all of that, and this all has to roll into how we design our dies. So a stamping die could be in the form of a progressive die, where we are going to feed a coil of steel through a die in incremental stations, doing a little bit of work in each of the stations until we get a completed part at the end of the die. Highly efficient, but these dies are expensive to build, they're expensive to maintain. But when high efficiency and production and accuracy is required, they can be an excellent choice as a process. Transfer dies can be processed in a number of ways. We can start from coil and partially produce the part attached to the coil strip, as we do in a progressive die. And then we may have to separate it from the strip and use some mechanical components in the die called transfer arms and transfer fingers. And we may have to flip the part over. We may have to rotate the part. It allows us to handle the part and put it into an orientation that we could not do if it remained attached to a progressive die strip. Sometimes we'll choose a transfer die because of the way that the blanks nest. If I were to make blanks in an offline blanking die, I might be able to nest those together much better than nesting them in a progressive die layout. So that means I improve my material utilization. And if we're working with expensive materials like stainless steel, for example, the material savings that you can experience from the nesting properly can offset the cost of having a separate blank die to blank those and then feed the blanks into a mechanical transfer die. We can also have single station dies or compound dies. These could be hand-fed or they can be tended by robots. Robots can move parts in a single operation, transfer them from press to press, or they can be moved press to press using operators. You don't see that too much anymore. 50 years ago, that was very common to have a line of presses and an operator at each press. But as you can imagine, that's a pretty expensive way to manufacture a stamping. So some sort of automation is typically employed today. And then the final piece of the puzzle is press selection. Now, oftentimes we will select the press based by its tonnage. We know that the press has to have a certain amount of capacity to handle the material that is being deformed. We need to expand our view of the press a little bit more to understand better. It has other capacity limitations, is what I'd like to say. It has other capacity limitations aside from how much force it can develop to make a part. One of these capacities is the capacity of the press to absorb reverse energy, or sometimes we refer to it as negative tonnage. This is the energy that builds up if I'm blanking, and we see negative energy or reverse tonnage situations. We're blanking or punching thick, high-strength materials. As the die is closing, we're building up a lot of force, right? And that force gets suddenly released, and we have this downward acceleration that we call snap through or reverse tonnage or negative tonnage, number of different terms that are used. But what we're seeing here is this sudden release of energy. So the example I like to use is, because we're all familiar, I'm sure, with using a 3-hole paper punch. So if I have 2 sheets of paper that I put together in my 3-hole punch, I can push the top of that 3-hole punch down pretty easily, and I can punch holes in my paper, right? Well, if I had to punch holes in 500 sheets of paper, that would take a long time, 2 sheets at a time, right? So I might, and I'm sure many of us have done this, I might take as many pieces of paper as I possibly can and cram it in there and push those punches through so I can punch more paper with each effort. But think about that effort. You really got to push hard on that 3-hole punch, right? I mean, you're really getting on top of it, and then suddenly all the holes punch through, and you might even smash your knuckles down on the tabletop because of all that energy is being released. Just like you hurt your knuckles on the tabletop where that hole punch is sitting, your press is experiencing the same amount of forces when it's exhibiting those reversals. The other parameter to be aware of is press energy. This is really important with deep drawing. Deep drawing. So if we're punching through a piece of sheet metal, the sheet metal might be 3 millimeters thick. So I'm generating some tonnage for a distance of 3 millimeters. But if I'm deep drawing a part that is 60 millimeters deep, now I've got to exert that force for a longer period of time, right? So we have to take into account press energy, because what happens is, because I'm working so much longer, the flywheel in the press is beginning to slow down and I'm losing energy out of the flywheel. And now I don't have enough energy for the next stroke to make the next part. So then the final thing is die maintenance and press maintenance. We have to make sure our presses are maintained properly. A poorly maintained press cannot be corrected in a die. I've seen dies that have big 3-inch, 4-inch guide pins in them, and heel blocks, and people say, well, the press isn't aligned, properly, hasn't been maintained. So we use the guide pins in the die to keep the die aligned. Think about this. If a guide pin or a leader pin, you may refer to it as a leader pin. If a leader pin could align the upper ram to the lower die, why doesn't the press manufacturer use leader pins to guide the press rams? Why such a complex gibbing system? It's because it's not sufficient. Leader pins, guide pins will deflect. And so you can put large pins in your die and the press is still going to deflect them. That is not the solution. Proper press maintenance is the solution.
Okay. Before we will speak about the tuning and material speed, we have some question here.
Okay.
Questions. So first one was from Preri Papataya. It's sometimes we have changed ST when coil change. If you are able to answer it.
I'm not sure what ST represents.
Okay. We have another question here. Hide it. It's still lots of compound die usage in the small consumer appliance industry. China labor still makes this process competitive.
Yes, that's absolutely true. I was speaking primarily in the more developed industrial areas of the world, where labor costs are quite high. Standard of living is quite high. The tendency is to use automation as opposed to labor. And so if you think about it, if you have work that you're having done in China, why? Because the labor costs in China make the process competitive there, right? And so the only way you could compete with that is you can't compete with labor, so you'd have to compete with automation. And then depending on the product and the volumes and the complexity, sometimes automation isn't a solution, or it's not economically viable, even though it could practically work.
Okay, and Pradeep explained something here about this question. He sent this one, that we are using high-speed press. Can you tell me how to control misfeed?
That depends on the speed that you're running in your press, but it's all going to be tied to pilot release timing. Pilot release timing is, I find, for press operators, is the number one thing that they struggle with, is getting the pilot release timing correct. And the reason for that is many times when we're looking at trying to set the pilot release timing. Now, one method of doing that might be, I'm going to begin closing up the die until I see the tip of the pilot just begin to open the or enter the pilot hole in the strip. At that point, I'm going to open the feed roll. I'm going to tell my pilot release to lift the feed roll. So as the pilot enters the material, it can position it. And so we may determine what that angle is. Let's say it's at 125 degrees before the bottom of the stroke. We set our pilot release for that timing, and then we start running the press faster. When we start running faster, we have to send signals to our feed system to, lift the roll, to feed the material. And there are delays, or there is a time that it takes for that signal to come from the press to the feed to the pilot release mechanism, whether it's a servo motor or a air cylinder, to tell it to open. So as the speed increases, we have to tell the pilot release to open sooner, right? Because there's that delay, or we call it a signal lag. There's a delay in the time that signal reaches the feed unit, and then the feed unit has to, if you've got a pneumatic cylinder, you got to activate a coil from a solenoid, a coil and a solenoid from a signal. You have to exhaust air from one side of the air cylinder, pressurize the other side, and all of that takes time. And if this lag time isn't considered when setting up for setting your pilot release timing, that's where companies get into trouble.
Okay, thank you, Michael and Predit, for these questions. Thank you, Pete, very much for the answers. And now we will speak about tooling and materials. So in metal stamping, tooling and materials selection directly impact product quality, tool life, and production efficiency. Choosing the right combination helps manufacturers reduce defects, extend tool durability, and optimize costs. So with that in mind, I'll hand it over to Peter Ulintz, who will dive deeper into this topic and share valuable insights from a design perspective. So go on, please, Pete.
Sure. So when we get into tool steel selection, this is all reminding me in 2 weeks, I believe, not to promote a seminar, but just because I'm speaking there. On April 9th and 10th, Precision Metal Forming Association is hosting a designing and building progressive die seminar. So a lot of things that I'm going to be talking about from here comes right out of that 2-day seminar. We spent a lot of time talking about these key tooling considerations, and one of the considerations is tool steel selection. So you may be familiar with materials such as D2, A2, M2. If you're doing a lot of high-speed stamping, you're probably using carbide inserts. But primarily, D2 is the workhorse tooling material in the tool and die industry. It is a good material choice for a vast majority of processes and things that we do. It's just that when D2 doesn't work, what do? Well, we can upgrade to a high-speed steel, such as an M2 or an M4. And these high-speed steel grades are also available in powdered metallurgy. These would be the PM grade materials. And these materials, as we get into the PM grades, they are kind of like a customizable materials. That's why there's a number of different grades. We can get some PM materials that have very high toughness, and we may sacrifice some wear resistance in order to get that toughness. And we're going to select these materials based on the forming failures or the die failures that we see in our tools. So for example, if I'm using D2 punches and they're chipping, so if I got punches that are chipping, You can see this punch here. I don't know how visible that is, but this punch is got a pretty large chip out of it. That could be a number of things. That could be a misalignment. That could be poor grinding practices. It could be a poor selection of material. But that I would actually refer to as breakage. Chipping would be much smaller, little chips breaking down on the edges. A tool steel will chip or break because it lacks toughness. So if I'm using D2, I may select A2. A2 has a higher toughness level. But people will say, well, but Pete, I don't want to use A2 because D2 wears better. Keep this in mind. You're not wearing out your D2 punch. It's breaking, it's chipping, it lacks toughness. Wearing isn't an issue. Toughness is an issue. So we want to select a material that has a higher degree of toughness. When we move into materials like PM M4 or PM3V, they're going to provide different levels of toughness and compression resistance and wear resistance. As a rule, what I suggest for people that are having difficulty with punch life in their dies, especially if you're cutting, punching, blanking, is choose the material that gives you the toughness that you need. And then you'll apply a die coating or a surface treatment to get the wear resistance that you need. So toughness first, and then wear resistance next, especially when we're talking about cutting and punching. And there's a variety of die coatings. Tin, tick, DLC coatings are just a few. There's aluminum carbonitrate. There's all kinds of different types of die coatings. I suggest working with your tool steel supplier and your coating person when you're looking at coatings. So I will say this, and at the end, I'll show some slides I have to better illustrate this. I'm going to go back to deep drawing. So for deep drawing, and let's say you've got an irregular shape, maybe it's some irregular shape. Oftentimes when we have fracturing or galling that occurs, a lot of times it happens in the corners, right? I'll have, you look at a deep drawn rectangular shell and the corners look really shiny, right? And sometimes they gall up. And so what we look at doing is, it's galling up. I need a better tool steel. We might change to tool steel. It gives a little better wear resistance. It's still galling up. Well, let's put a die coating on it. That'll help give us more wear resistance. Or we may even just take the lubricant and just spray that corner, and you get all kinds of lubricant in there. Remember when we were talking about deep drawing, how I explained that the flange thickens and that thickened material ends up going into the walls? Well, if you look at the four corners of a deep drawn box, if you would put those together, what do you have? A cylinder, a cylindrical part with a square flange on it. So those corners are going to behave like cup draws. The walls are going to get thicker. That's why they look so shiny. You're actually ironing the material. So before investing in expensive tool steels and in expensive die coatings, you might want to look at what kind of clearances that you might need in those corners to help relieve the pressure there. CNC programming, 3D CAD CAM cutting programming is great, right? It's fast, it's efficient, but oftentimes when we're machining complex contours, what do we offset our clearances by? Material thickness, maybe high limit of material thickness. But if you're getting into corners that are subjected to some compression in the flange, which means we're deep drawing, you're going to see some thickening in those corners, and our CAD CAM programs don't allow for that. We actually would have to go in there and reprogrammed to accommodate that. But many CAD/CAM programmers aren't aware of what's happening there. So we just cut the dies cut the data, and we don't change it. So we have to think about what's happening. And so that kind of rolls into the precision machining and maintenance as well. So precision machining, in terms of making sure you have clearances where you need it. The other thing would be maintenance, grinding, for example. I showed you this punch that was, all busted out. I don't know how well we can see that. There's and the face is all flaked off here. That face popped off. One of the things with this punch that was going on was the grinding for resharpening was very aggressive. And they were moving a lot of material at one time to sharpen the punches. One, because they were over entering the punch into the die matrix way too far. So they were entering like an eighth of an inch. So what would that be? I don't have my conversions now. I used to know these things right off the top of my head. But we may be entering an eighth of an inch deep. So we're probably looking at 3 millimeters. So 3 millimeters in depth. So if you chip the punch, you got to grind 3 millimeters off. Well, we started removing a lot of material at once so we can hurry up and get that ground down. In the process of doing that, they changed metallurgically the structure of that punch. At the end of the presentation, I'll have a micrograph to show you what's happening. We've actually reheat treated the very top portion of the punch. The surface underneath where we just heat treated, we actually tempered it. It's annealed, so it's softer. And then as we get to the body of the punch, it's the proper temperature. Thank you, Michael. So metallurgically, we're damaging the punch. So hopefully at the end, we'll have some time to look at those micrographs and I can explain it a little bit better. Material selections for stamping, we could be using mild steel and stainless steel, pretty common. Advanced high strength steels, these are the new steels that are being used in the automotive industry. They're lightweight, very high strength. Some of these materials have strength levels approaching the strength of your punches and dies that you're using to cut these materials. So the approach to processing advanced high-strength steels is very different approach. Many of these high-strength steels, especially the dual-phase materials, I'll speak just a moment really quickly on dual-phase materials, what that means. Most of the steels that we use, our mild steels, our high-strength low-alloy steels, are what we refer to as single-phase steels. If we looked at the microstructural phase under a microscope, what we would see is a ferrite matrix. It'd be all ferrite, iron. And it's a single, that ferrite is very soft, it's very formable. Dual-phase materials are primarily ferrite, but they'll have these small islands of martensite distributed all through the material, uniformly distributed. This martensite gives the material its high strength. The ferrite in it is what gives it its formability. That's why we can take today and have pretty high degree of formability out of very high strength materials. Now, that phase I mentioned was martensite. Where else have we heard the term martensite? When we heat treat tool steel, right? We heat treat tool steel, we austenize it, we quench it. And what's the microstructure that we have? Untempered martensite. Martensite is very hard, very brittle. So we don't just heat treat our tool steels, quench them and use them. What do we have to do afterwards? We temper them. We have to take that untempered martensite and temper it to give it some ductility, to give it some toughness. Untempered martensite is like an ice cube, right? If I take a hammer and I impact the ice cube, it shatters. and it's also very strong, right? That's the desired microstructure for tool steel is a tempered martensite. Now I'm cutting a high strength steel that has these little particles of martensite in there. What do you think that's going to do for die wear? Yeah, it's very, very abrasive material, very abrasive for cutting, very abrasive for forming. Again, this goes back to understanding behaviors of material and understanding material properties. Aluminum alloys are finding more favor, especially in automotive, for lightweight reduction. Some things about aluminum to keep in mind is aluminum has 1/3 the Young's modulus, or the elastic modulus, is 1/3 that of steel. So what that means for you as a stamper or a tool and die shop, what that means is for equal strength, for steel and aluminum of equal strength, because aluminum's elastic modulus is 1/3 that of steel, it will have 3 times the amount of spring back. So when we're designing dies, we have to take that into consideration. Now, the other thing about aluminum is it doesn't rust, right? We know it doesn't rust because the aluminum on the surface of the sheet metal interacts with the oxygen in the air. It forms a passive, tightly bonding oxide layer called aluminum oxide. Where else have you heard the term aluminum oxide? Grinding wheels, sandpaper, right? Abrasives. So aluminum, although it appears soft, it looks smooth. That aluminum oxide layer that's on the surface is very, very abrasive. This is why you experience galling in aluminum dies. A lot of times we think, oh, the material's soft and gummy. It's actually abrasive. It's abrading and ripping and tearing, generating a lot of heat and causing adhesive wear as well. So again, really important to understand the materials that we're working with. When we talk about die wear, again, we need to understand, is it abrasive wear? Is it adhesive wear? The reason for that is because the solutions are different, right? One way to know which you have, because you might say, because sometimes, without looking under a microscope, you might not be sure, is this adhesive wear or is it abrasive wear? If you have a condition where you're experiencing abrasive wear, if I were to take my punch here, I've got my punch here, if I were to weigh this very accurately, and after running in production, I weigh it again and the punch weighs less, it's worn out and it weighs less, it was subjected to abrasive wear. We abraded or wore away material. Material was taken away from the punch. If the failure is adhesive wear, the punch would, weigh more, right? So that's one way of knowing the difference between adhesive and abrasive wear. Fatigue cracking, that happens over time. One of the recommendations I would make, I would say do this all the time. After grinding punches, temper them. Temper them about 50 degrees Fahrenheit. I don't know what that is in centigrade, but here in North America, we use the rule of thumb. Whatever the previous tempering temperature was, temper them after grinding at 50 degrees below that tempering temperature. That'll do 2 things. If there's any retained austenite or untempered martensite on the surface from grinding, you will temper that, and the tempering will also restore, will relieve the internal stresses that lead to fatigue cracking. All right. Any questions in that area?
Yeah, there are other questions there. So this is the first one. In wire EDM machining of tool steels, I have observed stress-induced deformation and sharp corners. What best practices can help mitigate this issue?
Yeah. Okay. I was going to put a slide in to show at the end that related to this specifically, but we can talk about it. One of the things that happens with wire EDM is that, think about how you've got a hardened piece of tool steel. So it's hardened, it's tempered, and now we're going in there and we're going in with a wire. We are sending a high electrical charge in there that is basically doing what? We say it's cutting, we're wire cutting, but it's not a little saw blade that's going in there. It's very, very high heat that is basically evaporating the material as you're cutting it. Well, the same thing is happening as when you grind and you take off too much material. You're generating a lot of heat at the surface. So you set up a lot of stresses in a component that's been wire EDM. So two ways to combat that. Some companies will come and do multiple skim passes, so we get rid of that layer that has been reheat treated. Or you can send the die block out to be tempered again. Again, you'll temper it about 50 degrees Fahrenheit below the last tempering temperature to relieve any stresses that are in there. Now, the question here is that we notice it at the sharp corner. Yes, you notice it at the sharp corner because a sharp corner is a stress raiser. So if there's any kind of stresses, the sharp corner is going to fail first. The analogy I use for that is, if you've ever had, here in the U.S., we have a dried beef treat called beef jerky. I don't know, Mojmír, if beef jerky is something in Europe or not, but these tend to be packed in a vacuum sealed bag. And they're very difficult to open. But what the manufacturer does with the bag, and you may see this in other packaging, you'll notice that somebody will put a little notch in the corner of the bag. And if you pull right at that notch, it opens right up. No problem. Very easy. If I pull elsewhere on that bag, it's really hard to get it to open up. So if you've got a lot of stress that's focused in a corner, that corner is acting like that notch in that bag. As soon as I apply stress, and I don't need a lot of stress, I apply a little bit of stress, it opens right up. So if you've got a sharp corner there, you may need to look at putting a radius in there. There are techniques to cut a radius in the die block that's larger. Again, I present this in the die design seminar in April. I don't have a slide for it, but there is a method where we can put a relief notch in the die matrix to give extra clearance in the corner and strengthen that corner, and you still get a square opening in your stamping. Now, the slug looks a little bit different, but it doesn't matter. The slug is the scrap. So there are some things that can be done.
Okay. There are another questions, but we will answer it probably in the end of this webinar. So now we will speak about common challenges. As we know, in metal stamping, several common challenges can impact product quality, tool life, and production efficiency. Identifying and addressing these issues is key to reducing scrap, minimizing downtime, and improving overall manufacturing performance. To explore these challenges in more depth, I'll hand it over to Peter Ulintz again, who brings extensive experience in this topic.
Okay. Yeah, some key challenges, material cracking and tearing. This could be a material based problem. Could be lubrication issues, especially if you start running jobs faster. There's always a pressure in the press shop to increase strokes per minute or parts per minute. In doing so, keep in mind, as we begin to run the dies faster, the material that we're deforming, the faster we deform it, the more heat it's going to generate. That heat gets transferred into the tooling. So as the tooling begins to heat up, what do we know about metals when we heat up a metal? It expands, right? So if our dissections, let's think about it, if our dissections are expanding, what might be happening to our cutting clearances and our forming clearances? They might be getting reduced. So sometimes running faster, we introduce more heat, the die heats up, we can't make good parts, we have cracking, tearing. Throughout my career, we had a number of parts that were subjected to this. And what we would do is we would actually add cooling channels to the lower die section so we could actually cool the die while we were running at higher production. So where it might seem like I start running and now my material's not working, it might not be a material problem. And on the other hand, as we start to build more heat, our lubricants can break down. So where it may appear again that the material is failing when we're running faster or we're generating more heat, it could be a lubrication issue. So what you're beginning to see here is metal stamping is a highly interactive process. Everything affects everything else. It's not one thing standing on its own. That's why solving metal forming problems can be very challenging. Spring back and dimensional variability, we talked about that. I did some consulting on one job once where a company was experiencing actually two different scenarios. So one scenario was a lot of variability was seen in a particular stamping. The parts were to print, so the customer could use the part, but there was no so from an SPC standpoint, they weren't in control. So long story short, what happened is on one shift, lubricant was being applied to a die in one manner. On the afternoon shift, because it was much warmer in this shop, it was not an air-conditioned shop, an operator put a fan on the back side of the press and turned the fan on. Well, where it was blowing lubricant all over him. And so he turned the nozzle off of one of the lube sprayers. And turning that nozzle off at that particular part in the die changed the frictional characteristics in that station. It was a forming station. And so it changed the stress state in the part. And we had a little bit of different relaxation of that. So where somebody might think, we didn't change anything in the process, little things like that can make big differences. Another thing I will say for dimensional variability, if you are doing any deep drawing or forming where you have material that eventually you're going to trim away and it goes into the scrap barrel, oftentimes if we have splits or fractures that occur in that area outside of the product trim line where it's going to be in the scrap, oftentimes we'll let that job run. I suggest not to, because what happens is if you're collecting statistical data on these, you will find that parts that don't split may give certain dimensional results. Parts that have one split in, gave a little different results. Those that had multiple splits or longer splits, the dimensional results were a little bit. And the problem is you're looking at these parts and it's like they're varying all over the place and we can't determine why. And you can't determine why because you threw all the evidence away. It was probably the difference between having a split, having no split, having multiple splits. But now you can't track the problem because all the evidence is in the scrap barrel. So my suggestion is do not allow that to occur. Get the process under control. So die wear and premature failures, again, when we're looking at galling issues, make sure there's plenty of clearances in the die. If you've got chipping, wear issues, again, select a tool steel and heat treatment that solves your toughness problems first, and then increase wear resistance with a coating. And burr formation and poor edge quality, that's going to be directly a result of punch alignment, cutting clearances, and edge quality, how the part fractures. So one thing I will want to say about die clearances real quick, oftentimes I'll trick people, ask a trick question and say, what kind of cutting clearances do you use on your dies? And people say 10% per side, 8% per side. Oftentimes they'll have a number. There is no one number. It is going to vary by material type. So if we're looking at aluminum, you can't even have a cutting clearance for aluminum. Depending on the alloy and the temper, going to be different clearances. You can't even say for steel, depending on the strength of the material. Think about cutting clearance. Why do we put cutting clearances in our die? The cutting clearance serves as a lever. That clearance, the purpose of that clearance is to bend and break the slug out of the strip. We don't want to have zero clearance and extrude a slug out of the strip. We're going to have very high wear rates. So we put clearance in there so we bend that slug and have it break out. So when you look inside a hole, you can see here's where the cut band or the shear band is, and here's the die break area. As material gets stronger, we need a bigger lever, right? So we're going to need more clearance. Some of our advanced high-strength steels, 15 to 17% per side cutting clearance is the standard. I need a bigger lever to bend that slug. Now, the other thing to think about, too, are small holes. If you've ever had a part that had a pattern of holes, you've got larger holes, and then you've got some really small holes. Maybe they're approaching material thickness, and you'll notice that the cut band goes almost all the way through the hole. We don't have the same cut and break pattern as we have on all the other holes. It's because we need more clearance in small holes. And the analogy for that is, let's take a paper clip. If I take a paper clip and I straighten it out, that's pretty easy to bend, right? Now, what if I take that paper clip and I cut it so it's 3 millimeters long? Now I'm going to ask Mojmír to bend that 3 millimeter long paper clip. It's going to be really hard, right? I need a bigger lever. So smaller holes, we need increased cutting clearances. So we love to have rules of thumb. They work in a majority of situations, but we really have to understand the process at a deeper level to really solve some of our key challenges.
Okay, so now
you could look to see if we have any questions, and I'm going to try to pull up my other slides while you're doing that.
Yeah, we have some questions here. So
okay,
here is one. Oh, it's quite a lot. Wait, this is one. How do you view the transition from multi-stamping assemblies to gigacastings?
Well, it's here, right? It's here to stay. I don't. Gigacastings aren't going anywhere. There are issues with the fact that we can't. They're not easily repaired. But yeah, that's something that the industry is faced with. That's for sure.
Okay, so we have another question here. Considering the workplace environmental guidelines aiming for zero lubrication? What is the temperature threshold within the tool that could affect the properties of the cutting elements?
So, I lost something here. Oh, there we are. Okay. So considering the workplace environment. So if you're looking at zero lubrication, typically what the situation is going to be, it's not literally going to be zero lubrication. You may be using, so it might be zero liquid lubrication. You may be using a dry lubricant, a wax film. Some coatings for some punches have a degree of lubricity in them that will help to reduce our the wear and the heat that's associated. Processes might have to run slower. More clearances may be required when we're doing cutting and punching.
Okay.
But the whole issue is going to be heat and trying to mitigate heat.
Okay, so we have, for example, here there is a question from the beginning. Wait a minute. This one, I think that, thank you for the great knowledge, but sometimes we face misfeed issue in running time. Any sensor for avoid 800 SPE? You probably talk about it. You answer about the about the feeding before that, and the same guy.
Okay,
can you please send
So what I've seen in some high-speed stamping applications in terms of sensoring, sensors will be placed in the die to actually detect halfway through the progression. They'll have a sensor that's detecting halfway through the progression, a certain time period, that material should have progressed halfway to its stopping point. If it hasn't, then we use that sensor to stop the press, because then by the time the signal gets sent and the press actually stops, they were able to stop it in those scenarios. Another scenario, especially if they're short feeds. Again, I present this in the die design seminar in April. For a high-speed application, if you have a feed shelf where your material is, so this is an extension to the die, it's a lower plate and upper plate, and the material travels through the plate into the die area. We've milled out the top portion of that plate and positioned a sensor over top of it. And so what happens is if the material is feeding, and I got a sensor here, and I begin to feed and it buckles, I'll detect that buckle, and that sensor will shut the press down, because if the material buckled, it didn't progress on this end here, I know I'm going to have a short feed. So that's another option. So you can check halfway through the feed progression, or you can check on the entry side of the die, because if material is buckling, by cutting that opening in the top of that feed shelf, it forces the buckle to come up in that area. Some examples for press selection in, I'm not sure in terms of what. Selecting a press for what? Oh, did I lose you? Can you still hear me?
Sorry, now I was muted. Sorry.
Oh.
So can you mention about your life relationship?
Can you hear me? Okay.
Yeah. It's can you mention about thy life relationship with tooling material? Yeah, I think
so. Yeah, what I mentioned earlier before is don't select a tooling material based on its wear resistance. What's going to give me the best wear resistance? Wear resistance would be a good parameter if you're not having any other issues. But if you're experiencing wear of any type or chipping or breakage, again, you want to solve those. You want to sacrifice some wear resistance to solve those problems.
Okay, I think that was the last question. There are another much more questions, but I think it's a time to say goodbye, or if you want to say any say information about, please do it, Pete. And
okay.
maybe
we have like 3 more minutes. Do you see these slides?
Yes, we have 5 minutes. We have.
Okay, so if you see this punch here, can you see this punch? Can you see my arrow? Okay, you see these burn marks here on the punch? Mm-hmm. Oftentimes we'll grind a punch and you'll get burn marks, and then we'll come and grind those away, and it looks really nice, but the damage has already occurred. What this here is we're looking at the microstructure of the tool steel. What you see up here is untempered martensite. That material got so hot, it reheat treated itself, and it's not tempered. So you have untempered martensite, which I said is very brittle. And so if you're experiencing problems where, hey, I have a brand new punch, it runs for a long time. As soon as we sharpen them, the punches don't last long. Look at your grinding practices. And this got so hot that underneath this rehardened area, this got so hot that this is tempered. It is now softer than the base of the punch. So that's one way that we destroy things. My next slide here. I like to use the analogy I said before of a hamburger. When I make a hamburger smaller in diameter, its thickness gets thicker. So that means the thickness here, where my crosshair is, and that flange is going to get thicker, which means as it draws over this radius, that thicker material ends up in the wall. And we can see this when we look at forming simulations. We can look at the thickness gradients. And that's one of the reasons why we have to apply more clearance in the die. So at the bottom of this cup, this is a deep drawn cup. At the bottom of this cup here, the wall is 1 millimeter thick, 40 thousandths. That is the thickness of the blank. But up here at the flange, that flange measures 46 thousandths thick. So it's increased in thickness by 15%. That means we have to have more clearance in the sidewall here. And we can see this. I can get my next slide to come up. We can see this in this section of the wall. Look how this particular part, the wall is getting thicker, 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 thicker. That means we have to have appropriate clearance here. But look at the bottom of the cup. This was the original thickness, right? So what happened is this material was getting so thick on top of the blank holder, it was binding, trying to get into the die radius, that this entire wall stretched. It shouldn't be getting thinner, okay? This wall here, this thickness gradient, this wall is getting thinner. What it should actually be doing is, if I back up here, is getting thicker. 40 thousandths, 42 thousandths, 43, 45, 46. Again, I don't have the immediate metric conversion for that, but you can see it's getting thicker. As I also mentioned, stainless steel, some grades of austenitic stainless steels, you'll see thickening in the flange up to 40%. So if you don't compensate for that in your die design, you'll run into real problems. Okay. So that's really all that we have. There's no more questions. I thank you for having me, Mojmír. This was I really enjoyed doing this.
Yeah, it was excellent. I have some comments for you. It's from Nubar Korean. I've been into tool making trade for 50 years. Always respect your knowledge and contributions. Maybe one day we can connect a TIPCO. That's nice.
Sure.
That's nice.
Yeah, absolutely. And you know, some of the people that signed up for the webinar, I try to reach out and connect to some of you. If I haven't reached out to connect to you and you want to connect, feel free to send me an invitation. I'm more than happy to connect with people out in the industry.
Yeah, great. I'm sure that we need to do another webinar because there is a lot of questions and you know, I think that people like your knowledge, and you know, so maybe we will see if we'll do another webinar with Pete. I will do my best to continue with that, because you know, Pete has a great knowledge about stamping. So yeah, we will see. I will inform you in my LinkedIn profile. And for today, I think it's enough. So thank you very much. I really appreciate that you will with us, you join us, and especially I would like to thank you to Pete. Thank you very much. It was excellent, Peter. And yeah,
thank you.
If you want to say goodbye to the viewers, please do it now.
Yep. Thank you, everybody, for attending. It was a pleasure having you. If you have any questions, feel free to reach out to me on LinkedIn.
Great. Okay, so thank you very much. Have a nice day, and see you next time.
All right.
Bye. Bye.